welcome everyone to this week's Applied Math Colloquium. We're very happy to have Fruzsina Agocs here today from the Center for Computational Mathematics at the Flatiron Institute, where she's a postdoc and works on things with, I guess, as I learned, sort of historically, lots of highly oscillatory ODEs, more recently PDEs in periodic domains and point sources, and something she's going to talk about today. So, Fruzsina, go for it.
Yeah, thank you. Thank you for organizing this. Thank you for having me, and thank you for coming. So I'm Fruzsina. I'm at the Flatiron Institute. I work in the numerical analysis group, mainly with Alex Barnett. And today, I want to introduce you to some sets of methods. So one set concerns ordinary, and the other partial differential equations. And the theme connecting the two is oscillations. So oscillatory behavior of the numerical solution. In the world of ODEs, I'm going to be focusing on second-order linear homogeneous ODEs, and specifically, the extremely highly oscillatory limit. Whereas in PDEs, the focus won't be so much on the highly oscillatory limit, but on the specific geometric setup where the boundary is periodic and it has corners, and this introduces its own numerical challenges, which I'll explain. And yeah, in general, I'll introduce the problems, the challenges associated with them, why we should care, and then kind of lay out the field a little bit, the existing methods and my contributions, and then I'll dive into the methods, do some analysis, less detail on the kind of algorithmic implementation, so I'll refer you to the papers for the details, or you can ask me. And then some applications, and future applications where the methods can have impact and where they've already had some impact. Okay, so in ODEs, as I mentioned, I'll be dealing with second-order linear homogeneous ODEs, so things that take this sort of form. This particular one is phrased as an initial value problem, but I note that the methods do generalize to boundary value problems as well. I'll call this term gamma the friction term and omega the frequency because there is a unison here. Because this is the equation of motion of a generalized harmonic oscillator. And the assumptions are that these coefficients are real value, the frequency is non-negative, and I'm going to assume that the frequency is large and slowly varying for at least part of the integration range. And this will allow me to build an efficient solver for this differential equation. And of course, the computational challenge comes in the highly oscillatory limit. So if you were to solve this with a conventional polynomial-based method, meaning you're putting together the numerical solution from like piecewise polynomials, then the discretization length that you need to use goes as the wavelength. So at large omega, the discretization length is 1 over omega, runtime goes as omega. So at large omega, this is going to be prohibitively slow. On the other hand, it might happen that the frequency omega is large for some of the integration range and small in other parts. Gamma might get large, so you get a damped oscillator, in which case the numerical solution isn't oscillatory at all. And ideally, a robust numerical solver should be able to deal with both of these limits. So what I set out to do is build, in the first instance, like a 4/6 order and then higher order adaptive efficient solver that does not have this O omega runtime scaling, but is frequency independent in the runtime. Well, I believe that an important part of algorithm development is the implementation. So I also wanted to write user-friendly open source software. Well, part of the reason why I care about this problem is because as simple as this ODE looks, it's ubiquitous in physics and math. So in quantum physics, the time-independent Schrödinger equation takes this form, at least in 1D. My previous field, cosmology, has a bunch of these ODEs popping up. Special functions obey an underlying second-order linear ODE. quite a lot of applications, we end up having to solve these oscillatory ODEs, more than just once. So in cosmology in particular, where I used to work, I had to solve these as part of kind of a Bayesian inference. So I was exploring some sort of posterior probability distribution, and in each point in parameter space, had to solve several of these highly oscillatory ODEs, often ending up, needing to solve on 10 to the 9 times different ODE each time. So it didn't matter whether I took, a millisecond or a second in that solution. Right. And well, the other reason why I care about this problem is that there were no existing methods to deal with this. So there were some specialized oscillatory solvers built specifically for the highly oscillatory limit, but they couldn't deal with the solution being non-oscillatory and oscillatory in the same integration range. An example is Brauer's space function method, but he actually does have some new work on this, which is going to be working in the kind of less oscillatory limit as well. And then, of course, there are several asymptotic expansions for the highly oscillatory limit, familiar from quantum mechanics, but these are usually applied analytically, i.e. by hand, on a case-by-case basis, which is not feasible for like a Bayesian inference either. And there was no software available, period, especially not in kind of large numerical libraries, like SciPy, MATLAB built-in methods, that sort of thing. Right, so what I did is I first wrote kind of a 4-6 order adaptive method to solve this problem efficiently. The 4-6 order was enough because I only needed about 3 to 6 digits of accuracy in physics. And I worked on this with my old advisors from the University of Cambridge. And then recently with Alex Barnett, I generalized this to kind of be arbitrarily high order. So you can get 10 to 12 digits with the same efficiency. And I kept my word. I actually wrote software for both of these, and they were published in the Journal of Open Source Software. Right, so the general computational strategy in these methods and how they achieve this frequency-independent runtime is as follows. So I'm going to do time stepping. So I'm going to start from some initial conditions and follow along the numerical solution, adapting the step size h to keep a local error estimate below a user-specified relative tolerance epsilon. And well, the right strategy is, rather than to kind of blindly fit a polynomial to the solution, to exploit the fact that we know that it might be oscillatory and use something more suitable. This is what achieved the order one runtime. And this, what I'm going to do is do time stepping in terms of a slowly varying underlying quantity, which is going to be the phase function. So my methods use 2 different underlying sub-methods, one for the oscillatory limit and one for the non-oscillatory limit. For the non-oscillatory regime, it's going to be something like a Runge-Kutta or a spectral collocation, and the higher oscillatory limit, which I'll talk about in more detail, asymptotic methods. And then the part of the algorithm is that I'll have to switch between these 2 automatically. And the way I do that is I choose whichever method yields the larger step size for a given tolerance, for the sake of efficiency. And so a downside of using asymptotic methods is that, well, they're asymptotic, they're not convergent. So I cannot just kind of throw more compute at the problem and hope that their error is reduced. It might happen that there's an asymptotic turnaround in the local error before the tolerance is hit. And in that case, I can always default to the kind of old reliable, but perhaps a bit slower, Runge-Kutta method or spectral collocation. And this on the right is just an example of what I mean by the switching. So these blue crosses are they were taken with spectral collocation in regions when this numerical solution in black was not so oscillatory. But as soon as it becomes oscillatory enough for the asymptotic method, to be tackled by the asymptotic method, the method starts taking these really large strides, really large time steps. And this is what gives the kind of constant runtime with frequency. Okay, so I want to talk to you about these asymptotic expansions and start with the classic one. So this is called the Wenzel-Cravers-Brillouin approximation, or WKB for short. And I'll just talk you through how it's derived. So take the ODE and extract a small parameter, which in my case, knowing that the frequency is large, this is going to be applied in the large frequency limit, is 1 over omega naught. So you write it like this, and then do a variable transform, exploiting the fact that whether or not the frequency is large, the solution is going to have some sort of exponential behavior, either evanescent or oscillatory. So we do this kind of exponential variable transform, and then rewrite the equation in terms of x. And this is what I call the phase function. So it obeys this nonlinear ODE. And the hope is that in the high frequency limit, this x is slowly varying. So WKB proceeds by expanding it in powers of this small parameter 1 over omega. The coefficients multiplying the powers are these S functions. And by substituting this back into the ODE and matching powers of omega naught, you can derive this recursion relation for the S's. The important thing to note here is that in this recursion relation, all the previous terms are involved, which makes this a little bit messy algebraically. Let me show you why. So the way this is usually applied is these S functions are just derived analytically, and this expansion is truncated at some maximum j. But the recursion relation involves all previous terms, which makes this kind of messy. So these are the first couple of terms in the expansion, and it very quickly starts to blow up. I just wanted to demonstrate that this is an asymptotic expansion. So what I did here on the right side is I took a wiggly function, this black one, and I'm going to approximate it with kind of varying orders of WKB. So keeping a different number of terms in that asymptotic expansion, and then plotting the approximation in orange, and then its relative error in black here. And just watch what happens as I increase the number of terms. So 0th order, it's a terrible approximation. First order, it's actually already better. It gets around maybe 1, maybe 2 digits. And then as I keep adding terms, the error does subtly grow down, but then it goes up again. So the asymptoticity kicked in here, and if I were to keep adding more terms, the error would just blow up. Nevertheless, I mean, you see that this is not a bad approximation. It can approximate this oscillatory function for quite a few wavelengths. And this is what I'm going to exploit. And this was the basis of my first method, which I call Oscillatory. But yes, this is a very, very much an asymptotic method. Right. There's a better way of doing this. So in the kind of arbitrarily high order method that I developed, this is how it's done. So I'm still going to work in terms of this phase function x, but what I'm going to do is as kind of a functional iteration and defect correction. So I'm going to start from an initial estimate of the true underlying non-oscillatory x, and then add small corrections to it, and hope that it won't converge to the true solution, but it will go near it. The 0th order, my initial guess is going to be the same as in WKB, this plus or minus I omega. This is the true solution if omega is constant. That's what motivates that. And then from there on, I'll write down the residual of this underlying equation for x, which is called the Riccati equation, which is just what you would get on the right-hand side instead of 0 if you were to substitute back your answer. And then I'll add a small correction term to it, delta, which is a function, and write down what the residual of that corrected version is. And I'm seeking the delta of t, like a function that minimizes this, that gives a 0 residual. And if you were to just solve, this for delta, this is an ODE, and it has an oscillatory solution, so that's not feasible. But assuming that delta is a small correction, we can neglect the delta squared term, so linearize. And if we also assume that delta is not oscillatory, which we do want to keep it non-oscillatory, we want a non-oscillatory underlying quantity, then the delta prime can also be neglected because it's order omega smaller than all the rest of the quantities. And in that case, you basically just get an algebraic equation and algebraic update. So if you were to solve that, you'd get that in order to get the next correction, so from x0 to x1 and so on, you need the previous term and then the residual of the previous term. Which is very nice because this recursion only involves the previous term in the series. Not just that, but you basically just have to recursively apply this residual operator, which it does involve a differentiation here, but you can do that numerically. So the algebra is much less messy, and you don't actually need analytic algebra. You can just do it numerically. Anyway, so let me write down the first couple of terms that I did here and their residuals. And given some assumptions, the residual, it seems like the residual will decrease by order omega on each iteration. So if omega is large, this means it reduces the error very, very quickly. And what's nice is that we can actually prove this. So here it is working in practice. So I took an ODE, a very high oscillatory ODE, and I'm looking at the residual of this analytic approximation, much like I did with WKB with the Bigley function, as a function of the iteration number. And for each of the frequencies, I'm varying the magnitude of the frequency. For each of the frequencies, I get a geometric reduction in the residual. And you see that at the highest frequencies, which is this purple line, I very quickly get machine precision in the residual. So, and what's nice is that, well, we have a theorem about this. So we can prove that the residual is bounded by this geometric progression with a rate r. And the rate depends on the magnitude of omega, the frequency, and the rate of change of omega, which for asymptotic methods is somewhat intuitive. That's why I said that I require omega to be large and slowly varying. That's when that rate is going to be high. So this is the statement of the theorem, and the proof. I just wanted to outline the steps in the proof. The proof is by induction. So take some concentric nested set of disks in the complex plane, and I write down the residual of the next iteration in terms of the residual of the previous iteration in this asymptotic series. And the proof just proceeds by basically bounding these derivatives in terms of the function itself. So bounding rj prime instead of rj and xj prime instead of xj. You can do that by using Cauchy's theorem for derivatives and using induction, where you kind of decrease these disks. Anyway, right. So what I've shown you is this asymptotic expansion. But how does this connect to, how does this form a numerical method? So what we did is we got some nice approximation for xj, for this kind of underlying non-oscillatory phase function. But to get back to the solution of the original ODE, we need to undo the transformation. So that's what I'm doing here. That involves a numerical integral, or just an integral. In the asymptotic expansions, both WKB and this Riccati defect correction, which was the second one I introduced you to, you could have started from plus or minus I omega, and thus get two linearly independent solutions of the ODE. Because the ODE is linear, we can just linearly combine these to match any initial condition at the beginning of the step. And so we just do time stepping, matching the conditions every time. The local error estimate in this sort of method is just going to be given by the residual. To perform the numerical integral, here, and the numerical differentiation when applying the residual operator, I'm just going to use a spectral differentiation or integration matrix, typically with around like order 10 nodes. So this is not going to be very expensive. And this is just to go back to that previous example. And this wiggly function is the Airy equation. It gets progressively more oscillatory, and it gets difficult to plot at this point because all you see is black. But what I'm plotting here is the step size that the numerical method takes when being asked for 12 digits of accuracy. You see that the step size actually increases with the frequency linearly. Okay, I might skip over this slide because this is pretty standard stuff. So for the non-oscillatory regions, I'm either using the spectral collocation method, but you may use anything. Your favorite, run credit scheme, maybe even Otter's method. That's not a good idea, it's not very high order. But yeah, I'm going to probably just skip over this.
A naive question.
Yes.
So when your step size is so much higher compared to the period oscillation, how do I resolve the actual, when they
Yeah, really good point. So you can reconstruct the oscillations afterwards, because what you were doing time stepping in is the underlying non-oscillatory phase function, which you can interpolate very accurately using Chebyshev interpolation. And then from then on, you can just interpolate at any point and then do that transformation back, and you can resolve the oscillation.
So interpolation.
Yeah, yeah. So we can interpolate in the, not in the oscillatory thing, but in the non-oscillatory quantity. Okay, and just to showcase the state of the art, what I'm doing is I'm comparing my code's Osco, which is this kind of slightly lower order asymptotic method, and then Riccati, which is the arbitrarily high order oscillatory solver, to a standard high order Ramacata. And then these two methods kind of were developed since Osco. So, well, not converse space function, but WKB marching. And these are also specialized highly oscillatory solvers. And the example I'm using is this equation here, where again there's a parameter lambda that characterizes the frequency, and this is the example lambda equals 100, but I'm going up to lambda equals 10 to the 7, and I'm plotting the runtime of these various methods. And the thing to look at are these brown inverted triangles. This is the arbitrarily high order method, basically having a completely flat runtime as a function of frequency. And you see that the kind of lower order asymptotic methods all have this bump at lower frequencies. That is because they truncate the asymptotic series at a given point. And for lower frequencies, you actually need to include more terms in the asymptotic series to get the right accuracy. So in the lower frequency regime, they default to a Ramacata solver, and they will have this kind of linear increase in runtime for a while. Okay, and then some applications. So I come from cosmology. I mentioned that you often have to solve these highly oscillatory ODEs in a Bayesian inference setting, and one of the models of interest that has, before the development of these highly oscillatory solvers being completely out of reach, is closed or curved universes. And interestingly, these are now preferred by data, observations of the cosmic microwave background, but the models that had been considered before this were these kind of extensions of the current standard model of cosmology, which are not physically consistent. So they involve curvature as a late time effect rather than modeling the universe as curved from the get-go, if that makes sense. So, so these are these green and yellow lines, and then the red line is doing it properly with curvature from the beginning, and you see that the prediction for this is the current expansion rate of the universe is actually quite different depending on which one you use. So this was impactful. I'm also excited to use these oscillatory solvers for evaluating spherical harmonics. And in cosmology, pretty much everything is expanded in terms of spherical harmonics because we observe things on a sphere, on the sky. So the solvers that are being used in cosmology are quite fast. So in terms of floating point operations, but they don't parallelize well because they evaluate these special function spherical harmonics by recursion. So on the GPU, that does not give very good performance. Whereas if you were to evaluate them using just brute force solving the underlying ODE, that can be parallelized. So that's the hope. The kind of representation that I end up using for the oscillatory solution allows fast quadrature as well. So that's a future application, and it can be applied wherever in the literature WKB was kind of used analytically. Right. Oh, and that's just a fun animation showing a quantity associated with kind of how material in the universe is distributed as it gets progressively more closed. And this was, this sort of GIF was impossible to do before this. And let me just talk a little bit about the code. So software is associated with these methods is open source, and it's unit tested, documented, easy to install, and it's been peer reviewed. So there is a journal specifically for open source software called JOS, and if you submit there, they'll make sure that your code quality is up to the community standards. And these are just some screen grabs from documentation and like the examples of these codes. And I'm working with a software engineer to actually include these numerical methods in big numerical libraries, so it's easier to use for physicists and engineers. Okay, so that concludes
Before you go on,
Yeah.
I have one question.
Mhm.
So, when you switch between methods, what does that do in terms of errors and higher derivatives of the solution?
Yeah, good point. So the solution that I end up piecing together is C1 continuous. So that kind of tells you about the derivatives. So first derivative is going to be fine. Second derivative is also going to be fine. Third, not so much.
May I ask one more?
Yeah, of course.
Have you tried using this code on problems with more than 2 time scales?
So what do you mean? So already.
So suppose you have 2 modes of oscillation,
Uh-huh.
one much faster than the other.
If that sort of solution can be generated by a single ODE without a driving force, can it? Then I can apply it to it. I haven't tried. I don't know an example like that, but if that's a result of like a coupled set of ODEs, then that would owe one error. So even if it were possible to truncate the domain, you would probably need to include many kind of periods of the staircase, which makes this computationally not feasible. If I want to compute the solution from a single point source rather than some sort of quasi-periodic incident wave or a set of point sources, periodic set of point sources, then that breaks the periodicity of the system, which means that you can no longer do a periodization trick where you reduce the computation to a single unit cell of the boundary. I put a big red asterisk here because that's exactly what I'm going to do, but I'll explain how to do that later. And then finally, I'm interested in corrugated surfaces which have corners. These corners introduce singularities into the problem, which we have to deal with. And then, so some methods that are used for solving these problems are finite differencing and finite elements methods. There are mesh-free methods, which are similar to boundary integral equation methods. They deconstruct the solution into fundamental solutions, i.e. the solution in the presence of just a source and no boundary. Deconstruct them into plane waves. There are various approximation methods based on the Rayleigh hypothesis, which assumes that even in the grooves of the surface and everywhere basically in the domain, the solution can be deconstructed in terms of plane waves, which is not true in the grooves. And then there are some various other approximations like Helmholtz-Kirchhoff, which is like a ray approximation. So it's not true if the incident radiation is of a similar, like the wavelength is of a similar scale as the grooves in the surface. So what I ended up doing is developing a high order accurate method based on the boundary integral equation. And this is, the paper is fresh out the oven. It just hit the archive this morning.
Wow.
And the reason why we're considering boundary integral equation methods is because as the name suggests, the equation will live on the boundary. So I only have to discretize a 1D surface instead of a 2D domain. So the computational complexity is much reduced, and the singularities can be dealt with to high order accuracy with high order portraiture. But I'll explain this in a second. Okay, so this is the mathematical formulation of the problem. So what I want to solve is this, I want to solve the PD and this domain omega. This is a single unit cell, like a repeating element of the boundary, which I'll call gamma. The periodicity is D. And here's our point source is X naught. Our incident field is UI, and the scattered field is US. These are scalar field non-vector fields. What the acoustic pressure, total field U, which is the sum of these two, obeys is the Helmholtz equation. And I'll first consider the quasi-periodic problem. So on the right-hand side, I have not one point source, but a set of point sources, which are all separated by this periodicity D. The boundary conditions on the surface are Neumann, which means that this surface, it reflects sound. It's sound hard. And then I'm going to impose quasi-periodicity, because if the incident field is quasi-periodic and the boundary is periodic, then this whole solution needs to be quasi-periodic. And finally, I have to impose a radiation condition on the outgoing wave in order to not to get unphysical blow up in the far field. So the quasi-periodicity is it's associated with a wave number. So the incident radiation has some on-surface wave number associated with it, and quasi-periodicity means that if I were to move in the solution by one period D, then the whole solution can only change by a complex phase e to the aggregate kappa, where kappa is this on-surface wave number. Because of quasi-periodicity, there are several kappas that lead to the solution looking the same. If I were to change it by 2 pi n over d, the solution would look exactly the same. But then if I were to preserve the total wave number of the incident radiation, which gets broken down into on surface and kind of away from surface, then that means that the wave number of the solution going away from the surface can either be real or imaginary. So it either can propagate or it's evanescent. I'm mentioning this, and this is important to mention because at the boundary of those two behaviors, there is a discontinuity, which is it's referred to as a Wood anomaly. And basically, this boundary integral equation method will break down at those Wood anomalies. But not to worry, we're going to go around Wood anomalies.
Before you go on,
Yeah.
just back a slide.
Mhm.
Usually, when you see diffraction pattern,
Mhm.
that's a similar problem. And when do you see this evanescent wave? Which one of these are your large list on the right produce propagate evanescent wave?
So
Meaning that the wave that's propagating along the surface.
So the waves that propagate along the surface, they have a large kappa n, so they have a large wave number in this direction.
Wave number of the grading itself, of the step size, or
So
I missed that, yeah.
so the wave number, let's phrase it in terms of wavelength. So the wavelength of these trapezoids that propagate along the surface, they're going to be similar to D.
Right.
Right.
So the same, yeah.
Yes.
So that's in the diffraction limit. And I guess I'm missing a little bit. Somehow they, usually in the diffraction limit, we only look at things that end up in the image. I guess we don't think about necessarily what allows it to constructively form this coherent wave along the surface. It's something known, obviously, but I didn't know. So I was hoping that. but it seems like it's not particular limit. When the incident wave at the wavelength that's comparable to the grading periodicity.
Yeah, then you don't get a far field. Yeah.
So then you get, if you think in that limit, in this case, when you incident on it, because it's not transmitting, and then somehow the reflection part might, I don't know.
So some of it is
It's
still
really-
reflected. So I'll show how like the incident power is distributed
Yeah.
among the track modes and kind of the outgoing radiation.
Yeah.
And there will be some outgoing radiation. It's just going to be much less than what you injected in the system. But basically, the incident radiation excites some of these track modes, but it will also include, it will include frequencies where there are no track modes. So yeah, you'll get reflection. I hope it becomes clear by the end. I'll show you like a full scattering picture. Okay, so just a very quick introduction to boundary integrals. So boundary integral equations work by converting the PDE into a dense linear system. And the way that works is we model the scattered field as a scattered wave with something called a single layer potential. This means that we kind of deconstruct the solution in terms of fundamental solutions. Fundamental solution is this phi p, which is also called the quasi-periodic Green's function, and it's just the solution of the PDE without the boundary. So just the sources, just in the presence of a quasi-periodic set of point sources. This is not that important, but basically it ends up being the sum of Hankel functions. I'm not going to go into how that's computed. It's beyond the it's a bit too technical. But the point is that this representation, the single layer potential representation, ensures that US, the scattered field, satisfies the PDE. And what we need to do after that is substitute this and impose boundary conditions as we approach the boundary, the surface. And that gives an equation like this, where dt is the adjoint double layer boundary integral operator, which is this thing here. If that's too much, the thing to take away is that this only exists on gamma, which was this boundary of the unit cell. So this no longer lives in a 2D domain. This only lives on the boundary. So this is still an integral equation. It's called the Fredholm integral equation. And on the right-hand side is something to do with the boundary condition. But this is still kind of nasty to solve, so we're going to discretize it. And that's what gives you the dense linear system in terms of this unknown density sigma. And once you solve for sigma, you can substitute it back into the single layer potential representation and reconstruct the scattered field anywhere. The discretization is like where the challenges arise, right? How do you choose the discretization points on the surface? I'm going to use something called Nystron's method. If you're interested in the details, I refer you to the Colton and Kress famous textbook on this one. But the point is that we are going to replace the integrals by quadrature. So we are going to associate with the boundary quadrature nodes and quadrature rules. This would have been useful to show earlier, but basically this is what the fundamental solution looks like. If your point source is as a source y, it's a function of two things: the target position and the source position, and it just looks like this. It's and then for a surface with a constant density sigma, this is what the field looks like. And the point is that the scattered field is deconstructed in terms of these sorts of waves. Anyway, so how do you discretize the boundary? This is what the boundary looks like. And the tricky point is here, because in this corner, we have to evaluate this quasi-periodic Green's function or this fundamental solution as x approaches y, and that, well, it is singular there in this corner. So in order to preserve accuracy, what we need to do is kind of refine and put cluster more quadrature nodes into the corner. So what we're going to do is panel quadrature. So we split the boundary into these panels, equally sized panels, and then we do dyadic refinement or triadic refinement, where we split these panels into smaller and smaller panels adjacent to the corner, and then we lay down Gauss-Legendre quadrature nodes onto each of these panels, and we associate Gauss-Legendre weights with them. In this geometry, this is particularly easy because these panels that are next to each other, they're collinear. They don't end up contributing to they only end up contributing an identity to the dense linear system. Otherwise, you need to do some special stuff. Okay, but basically now, I've introduced the entire methods of solving this integral equation. So let's talk about what trap modes are. So we had a Fredholm integral equation which turned into a dense linear system, and it had something on the right-hand side here. Trap modes arise when there is a non-trivial solution for a sigma. So there's an eigenmode associated with the eigenvalue 0. So there's a solution, non-trivial solution sigma with the right-hand side 0. This is not a kind of a mathematical, like a spurious resonance. This is actually a physical mode. And these are some examples of what that looks like physically. So what I'm plotting here is the acoustic pressure field around the boundary. And so these are the modes that propagate along here, along the surface, but are evanescent away from it. And this is like a larger wave number mode, and this is a smaller wave number mode. And you see that the larger the on-surface wave number, the more trapped the mode is, the kind of closer it stays to the surface. The way I go about finding these modes is I need to look for pairs of kappa omega, where omega is the frequency of the incident radiation, and kappa is this like on-surface wave number, where the determinant of this matrix is singular. So that means I'm looking for zeros. I'm looking for roots in the determinant. I can do this via root finding, and this is precisely what I do. So fix the incident frequency omega, and sweep over all possible wave numbers, which goes from -pi to pi, and do root finding. And what I'm doing is I'm computing the location of these roots, which gives the dispersion relation, and I'm going to take the slope of that dispersion relation. That gives me the propagation speed of these trap modes. It's called the root velocity. And then finally, once I have the velocity with which each of these trap modes propagates, I can do a very simple array model and compute the arrival times of different trap modes at the bottom of the staircase. But let me show you the results. So
What's
this.
the difference between the two pictures that you showed?
Yeah. So this is a trap mode associated with kappa equals pi. So this is the kind of extremal trap mode. There is one lobe in each groove, and this is a smaller, it's a smaller wave number trap mode.
I'll ask later.
Okay. Maybe this will. So this is the location of the trap modes. So what I'm plotting here is, for each incident frequency, what is the horizontal wave number? What is this kind of length scale associated with a trap mode, if there is one? And what you see here is that above a certain frequency of the incident radiation, there are no trap modes. So if the incident radiation is such high frequency that you would need to fit like multiple of these lobes into each of the groups, that does not exist. You cannot satisfy the boundary conditions like that. So yeah, this is the dispersion relation. There's a critical frequency above which no trap modes exist, and this is how quickly they propagate. And you see that in the limit of kappa going to pi, so these guys, they actually don't propagate at all. Or they are very, very slow. Their group velocity is 0. And these less trapped modes, the ones with the kind of big, like long exponential decay lengths, they are very quick to propagate. And what this means is, if I were to clap at the top of the staircase, and I will assume that that clap excites all trap modes equally, and I make simplifying assumptions like, the wave packet does not disperse in the third dimension and so on, then the frequencies of the trap modes that arrive first are going to be the low frequencies. And these high frequency modes arrive last. And that explains that chirp phenomenon. So let me show you what that looks like. So I reconstructed, I took the parameters of that nice step pyramid that I showed you at the start, the Castillo pyramid, and I'm plotting the arrival times of all trap modes. This is what it looks like in terms of human, frequencies, like in hertz. And I just wanted to show you what it sounds like. Did you hear them?
Yeah.
Yeah. It's a bit like a raindrop. Right. So, this is kind of an experimental mathematical verification of that raindrop phenomenon. Okay, and this is the finish line. This is going to be the last part of the talk. So we talked about trap modes, and now I'm going to show you how to compute the solution for a single point source, the scattered solution of a single point source. But what I've been dealing with so far was an incident, like a quasi-periodic incident wave. Okay, so the main trick here is that you can write a delta function, i.e. a single point source, in terms of an integral over this horizontal wave number of a sum of delta functions, i.e. quasi-periodic sets of point sources with quasi-periodicity e to the I n k kappa d. This is just, you can check this, it's true, check the algebra. But because of the linearity, it means that the solution can also be written this way. So the scattered solution from a point source can be written as an integral over kappa of these, solutions associated with quasi-periodic sets of point sources. Okay, but the bad news is that this is what the integral looks like. So I complexified the integration variable kappa, but the integral needs to be, this is over the real line. And on the real line, there are some dangers lurking. So there are two poles, and there are two branch cuts. The poles are associated with the trap modes, and the branch cuts are those wood anomalies that I talked about, where the wave going away from the surface goes from propagating to evanescence. And I'm indicating the direction of the branch cuts. So basically, if you were to perform this integral, you need to somehow deal with these poles and branch cuts. And the way I'm going to deal with them is by contour deformation. So this integral is taken in the principal value sense. So it goes, it's in the limit of going around the pole, but the radius of the little semicircle around the pole goes to 0, which means I can deform the contour and kind of increase the amplitude of that little semicircle without changing the value of the integral by Cauchy's theorem. So basically, this integral becomes an integral over the sinusoid. And this way, I'm avoiding both the branch cuts and the poles. One needs to be careful to go around the right way. So it's not a coincidence that the branch cuts weren't chosen to be in the opposite direction, because that would correspond to waves kind of going towards the source rather than away from it. I think I have an animation showing that. I hope that will play. Yeah, there we go. So just a sanity check that I've gone around, that I've deformed the contour the right way. Here's my point source, and this is the real and imaginary part of the total scattered solution. And you see that these lobes are they're going away from the source. This is the physical solution. Okay, and so I did this contour deformation, and I'm going to replace the integral with quadrature, and I'm going to perform, I'm just going to use a trapezoidal rule with PASM nodes. The ASM stands for array scanning method, because this using this integral is called array scanning in engineering, or Fouquet block Fouquet in mathematical physics. Okay. Right.
So one thing I noticed is the amplitude of the intensity as they propagate, that remains constant. It doesn't decay as it forms point source, which is very nice.
Yes. So that's, yeah.
That's probably, a nice thing about why all the application you were saying. earlier.
Exactly. So that's the waveguiding property, in that, these trap modes, they just transport power away.
Yeah, without
they don't.
changing intensity.
Yeah, exactly.
For the point source.
This is the waveguiding property, and this is not a trap node. This is just this is the full scattering problem from a single point source. But you see that the solution is, as you go further away from the point source, it seems to be dominated by the trap modes, right? And I'll show you why that is. But first, convergence tests. Okay, yeah, I know I won't. Maybe I won't talk about convergence tests too much. But the way to verify this, that this method works, is, well, we don't have access to the analytic solution. So we could do slab convergence, which may be misleading, or we can look at a conserved quantity and see how well it's conserved numerically. There is something that's conserved, which is the kind of total flux going out of the system. And if I look at how many levels of boundary refinement, so how many panels I lay down, plot how well the flux is conserved, you can see that I can get 10 digits. And this is doing the same convergence test, but in terms of this array scanning contour deformation. You see that it's actually quite sensitive to the exact amplitude of that sinusoid, but I can again get machine precision here. Okay, so the last thing, what I wanted to compute is the power distribution in trap nodes. The way to do that is to look in the limit of going infinitely far away from the source. And my claim is that in the far field limit, in the far away limit, the only power transported away from along the surface is in trap nodes, right? And you can see that as follows. So I plotted this array scanning integral, but instead of plotting the solution in the central unit cell, what I'm plotting is the solution in the nth unit cell. So the integral in the array scanning, it gets this extra e to the in kappa, which induces these big oscillations in the complex plane. I'm going to close this contour in the limit. So I'm interested in the n going to infinity limit. So I can no longer do this integral numerically. But I can close a contour, and I'm going to close it if n is positive in the upper half plane, and go around the branch cut like this. And you're going to have to believe me that this part of the contour does not contribute to the integral. This one does not contribute, and these two cancel. So this little semicircle also does not contribute. So what that means is the value of this integral, the array scanning integral, is just going to be the residue of the pole, i.e., which we know is the trapped mode. So infinitely far away, the entire field is just due to the trapped mode. And if I compute the flux going kind of sideways in an infinitely far away unit cell, then that is also expressed in terms of the residue at the trapped mode. So this is how you extract the power distribution. And if I were to compute that kind of power distribution in terms of the horizontal wave number of these trap modes, that's what that looks like. The thing to look at is this black line, the trapped fraction. So how much of the injected power in the system, the power injected in the system, is transported away. And you see that as these large wave number trap modes, i.e. those ones that had the really short decay length, that were like really staying in the grooves of the periodic surface, they transport away almost all of the power. So this approach is one, but they are very slow. Their group velocity is very, very slow, but they're very efficient at this. Right, okay. So in terms of future work, what I'm interested in doing is, well, what happens if the source approaches the boundary? How does that affect the power transported away in trap modes? I'm guessing that if I move the source further away, there's not going to be as much power in the trap modes. It'd be nice to build a physical model around this, so I can get in these waveguide applications, physicists and engineers can get a good idea of how close they need to be, how close the source needs to be to the surface. Okay, I'm also interested in what happens if the staircase is not symmetric. So what if the stairs, are on one side are shorter than the other? Do we get asymmetry in the power transported to the right and the left? I'm not sure. Also, care needs to be taken in performing the array scanning integral when the on-surface wave number of the trap modes approaches 0 and plus or minus pi. That's because the poles associated with them are going to get close together. So the quadrature, we need to place more quadrature nodes in this array scanning integral. I'm also interested in exploring 3D periodic surfaces, in which case that array scanning contour might get quite complicated because poles become lines, branch clouds become kind of planes or surfaces. And maybe this could also be used for fault detection in photonic crystals, in which case the trap modes maybe don't exist, or maybe they don't transport as much power. And yeah, this concludes my talk. Thank you. I included the blue jay because, well, they get their blue color not from pigment, but from periodic, from the band structure of their feathers.
We did have a number of questions during the talk, and we ran slightly over, so I think it might be best if we take further questions up front, Fruzsina, and there's also refreshment. I'm saying there's refreshments, I hope there's, okay.
True story.
Phil's nodding, and then there's refreshments in the cam space after. So what do we think? Fruzsina again.